case are not much because you are just in the L2 space. So that makes a lot of sense. Now, the ball game the goalposts begin to shift a bit when you are looking at a multi-class problem. Because in the multi-class problem, it's not really like the binary case. And most of the time, you're not just going to be doing binary issues. You're going to be likely faced with a lot of other classes. There are situations where you could even have up to 1,000 or even 1,000,000 categories. And then you're supposed to sort these out. So the more the classes, the more the complexity. And remember what I told you guys, that what happened is that um, on the on the number line plane, or the XY plane, we only consider this the Y and then the X plane. That's this plane here. Now, the issue with multi-class is that you are not dealing with just two categories that you could easily, just draw one line and then you say it's either a white or black or red or yellow. No, in this case, it's kind of you have other classes. So imagine when you have three classes. It means when you drew the first one, you have to drew another one to separate it and also drew another one. So imagine if you have up to five, you are still going to try to be able to differentiate them from the other one. So the more you increases them, the more the complexity comes into play. So the multi-classification assign the inputs to one of the several categories. Unlike the binary classification, which deals with just two classes, it differs from multi-label classification. It involves predicting multiple categories. Yeah, we clarified that in the last class. So if you have not watched that, our last class, you could, no, I think a class before the one we did last week. If you have not watched that, we talk about the multi-label and the multi-class issues where we delved into the practical section of these classes. But today we're not focusing on the data type problem itself, but the matrices that we're able to evaluate them. Now, consider, for example, this is class A, class B, class C, and class D. So you're looking at a problem that have four different categories. Now, and you want to be able to make sure that what you're doing, it makes a lot of sense. So choosing the right approach, again, will depend on the characteristic of your problem. And also, you have to integrate issues that are also very important, like the domain specific. What is the hypothesis of interest? What are the things that you want to explore or test? And then you'll be able to settle down for the best algorithms to use. When having considered the best algorithms, you will now bounce back to the choices. In the case of multi-class problem, what you are going to be interested in is the micro averaging, the micro averaging, and the weighted averaging. Now, the macro averaging averages the metrics across all the classes equally. So it means that when you are looking at recall, precision, and F1 and all that, what you're going to do is you consider all of them that are being scored, you aggregate them, and then you take the average at the end of the day to see what you have. But in the case of the micro averaging, you aggregate the predictions individually to compute the overall performances. So in this case, you looked at what is the precision, for example, in class A, what is the precision in class B, what is the precision in class C, before you now be able to do that. So it's not the one that you iron out everything across, but rather you look at them. So that's why we say micro. So micro is like an individualistic. You zoom into it. I remember those days we do biology. We talk about the microorganisms and also the macroorganisms. Cell, I think, then they told us it's a microorganism and stuff like that. So the same thing. So in this case, you're zooming into each of these metrics and then you aggregate them at the end of the day to compute the overall. But now the weighted on the other side, it assigns weights on these metrics based on the class size. It makes a lot of sense because when you are dealing with imbalanced classes, remember, like I used to say, the classes of interest may be rare occurrences. So they're usually going to be marginalized, sort of. So because of that, if you don't assign some sort of a weight to them, they will go on unnoticed in the contribution. And then when you're making decision, you're likely not going to consider them. For example, in the case like when we talk about democracy in the world, we talk about the game of numbers. But that does not mean that democracy should ignore equity. Okay, because some people could argue more and say, oh, democracy should just focus more on equality. But if you don't stress also on equity, it means that underrepresented people, their voices will not be heard. And that's not how it's supposed to be. If you want everybody's voices to be heard, it means you have to look at making decisions even at micro level so that everybody will be inclusive in your decision. So that's similar way when we talk about these matrices. You have to make sure the metrics you are using, again, it depends on your data set, but make sure it is the metrics that take care of some of these nitty-gritty things that could arise. So when you are looking at accuracy in the case of the multi-class problem, the accuracy provides an overall estimate of the model quality, but ignore class balance and error cost. So high accuracy can be misleading in an imbalanced dataset where the model favor majority classes at the expense of the minority ones. So like I told you guys earlier on, the accuracy can be deceptive when you have imbalances in your dataset. So you can have a good score of 96, but excuse me, is it 96 what? Is it 96 of everything or 96 of some persons? So these are some of the things you have to look at. For example, looking at this problem here, when you have that four classes that we talk about, A, B, C, and D, you can see that in this class here, B is highly underrepresented. So you could see that among the prediction of C is not doing so well. And the reason is because when you look at the total prediction of C, you could see they are not much compared to the other classes. So B and C are highly underrepresented compared to D and A. So if you're looking at your model that you have 96, 96 of what? 97 of what? 95 of what? Is it 95 of everything or 95 that you have just one person that was predicted right or one target that was gotten right in B out of 1, 2, 3, 4, 5? It was only one that it got right. So can you call such model to accurate? So these are some of the questions that you have to ask yourself. That if you have a situation of highly underrepresented instances or imbalanced classification problems, then the accuracy cannot be trusted because it could really mislead you and make you, look like you are doing something nice, whereas you are having some models, some instances that are highly underrepresented. So that kind of democracy is not the right one. So that's what we talk about. So in this case, you have to look at equity as well and say, oh, my model is doing well, but it's not detecting the classes that are underrepresented in it. So on the other hand, when you are looking at calculating the precision and the recall in a multi-class problem, if you're calculating it by class, is useful when specific classes require detailed evaluation, especially in imbalanced dataset where minority classes performance matters. It helps assess how well a model distinguished a particular class. Like I said, you have to look into the performance to see what is happening underneath the hood on each of the classes. So zoom in and look at them. For example, looking at the recall and precision of class A, you could see the recall is 87, the precision is 72. Great, it's doing well. But when you come to class B, which is the one I highlighted here, you could see that 33 in the recall and the precision is 20. So if you look at it, this is not a good score. This is quite bad. This is not right. So can you really say that your model is doing great? despite the fact that you have a class that the detection is very, very small. The same thing happens when you come to C, you have 90, 90, which is nice. D also is 993 and 100, which is great. But now we have a class here that is underrepresented, and it's also the prediction was not doing well. It was only one that was captured. So that kind of a problem, it it requires you to go back and look at it very well, check it, evaluate it, and say, no, something is not right. So we say, however, for a large number of classes, individual matrices can be overwhelming. In such cases, the macro, micro, or weighted average provides a more concise summary. So this is where the macro, micro averaging comes into play, because we cannot focus on just the individual predictions and then we make no, because that way we will miss it out. So the macro averaging would take these cases into consideration. So it's not just going to sum them based on individual, but it will sum them across it. So definitely, it will drop, because by the time you add 33% or 0.3, you add 0.87, you add 0.9, you add 0.93, and you divide them by 4, you will definitely have a drop. You are not going to have this beautiful 90, 80 something. Probably you have around 70 or thereabout. But that shows that your model, is not discriminating the ones that is not represented. So the macro micro averaging help us to be able to take care of these classes that are not instances that are not represented much in the class. So we said when to use the this multi class matrices, the macro averaging. It's best to use it when all the classes are equally important. Like I said, when all of them are important, you cannot focus on one and leave the other. So you have to make sure that what you are looking at is putting everybody into consideration, not just some persons, but everyone. So the macro averaging work best when all these classes are important to you and you have to make sure you take all of them into consideration. But the micro averaging is ideal when the total classification errors matters most. So because at the end of the day, you will really look at which one is really giving me this issue. Can I be able to upgrade it? Can I be able to help it out? So that will now bring you to begin to see if you can impose some sort of weight or some sort of conditions to improve the performance of the model. Some people can even go ahead to perform things like oversampling, undersampling, smooth sampling, and all that to see if they can move or improve the performances. The weighted averaging is useful for imbalanced dataset to avoid bias towards majority classes. Like I said to you guys, you have to be careful of the majority classes dominating the minority classes, because the majority classes are very, very most of the time they may be the negative classes that you are not really interested in. The example we talked about in the other day on fraud detection, when you looked at that data set, you will see that it is a data set that is highly imbalanced. Because it is highly imbalanced, it will not make sense if most of your decisions are favoring the non-fraud cases. You are interested, for example, to build a model that is able to predict a fraud case. So immediately it sees symptoms of fraud, it's locked, for example, the model. But the moment you build a model that it's always saying it's not fraud, even when it's fraud, then there's a problem, because a lot of the fraudsters will get away with their evil, and the model will not flag them down. So you have to make sure that you're able to build a model that when it sees fraud, it will say this is fraud and it will flag it down. So consider domain-specific interest when selecting the metrics. So like I said, what is your hypothesis? What is the hypothesis you are interested in testing? And the testable hypothesis is very important in helping you to select the right matrix. It's not just everything that you're interested in. So sometimes you have the specific question in mind that you want to answer then. And based on that question, that's what is going to determine the kind of metrics you want to use. So what is then the macro averaging? Remember, we talked about the macro averaging and how beautiful these things are, and we could use them, but we still haven't talked about what they mean. So consider, for example, your confusion matrix, like we talked about. Remember, we always go back to the confusion matrix because it's very important in helping you to understand some of these matrices. Now, remember, we talk about the actual values are here, and then the predicted values are here, the ground truths are here. But anyway, irrespective of where you put them, you're going to have the true positive, the false positive, the true negative, and so on and so forth. Now we say Tn is the true positive, Tp is the true, Tn is the true negative, Tp the true positive, and so on and so forth. Now we calculate the number of true positive, the false positive, and just like we did in the previous class, we also compute for precision and recall. Now, in the case of the macro averaging, we will add the precision of class A plus the precision of class B plus down to the precision of the last class. And then we divide it by the total number of classes we have. So if we have 5 classes, it means we are going to have class 1, 2, 3, and 4, 5, and then we add their classifications, their performances scores. In this case, if it's precision, we are going to add. And now we remember when we talk about the precision, we said the precision talk about the rows, the recall talks about the column. So it means you're going to add these rows, remember? Then you divide. So you do for class A, for class B, down for class C, and then you aggregate it. Then the same thing you do for recall. The recall of class A, the recall of class B, down to the recall of class N, divide by the total number. So you average both the precision and recall across the classes to get the final macro average precision and recall scores. So that's how or what the macro averaging means. Then, what does the micro averaging mean? First, in the case of the micro averaging, remember we said it's more focused on individuals. So you have to first calculate the total number of true positive, true false, the true positive, the false positive, the true negative across all the classes. Then you can now sum for each of the classes. So the total number is sum of true positive counts across the classes. You do true positive counts for all the across the classes again. You do for false positive. You do for the total negative, and then you could be able to. So here is the catch. So it means that TPA for class A, you add it up. You add that of TPB for class B. You do that for everybody, and then you divide it by the total of all of them. So it makes a lot of sense that the micro average takes a different route. So most of the time, you're likely going to see a different scores when you see the summary of the performance for the micro and the macro, and it's because each of them follow a different route. Remember, the macro gets the classes and aggregates them, but the micro will go inside them for each of them. So the true for A, for B, for C down to N, it adds across, it aggregates across. So the same thing you do for the recall. You get the TPA plus the TPB and all that, and then you average everything. So to calculate the precision, you divide the true positive by the sum of the true positives and the false positive. For recall, you divide the true positive by the sum of the true positive and the false negative. So that's how you do that. Okay, I think there's a question, John.
Yes, Doctor, I realized that the formula for depreciation and recall, in this case, they are the same. Am I not seeing it right away?
No, they are not. Remember that the the precision talks about the row. The
Yeah.
recall talks about the column. So now let's look at it. This is TPA, TPB
PB.
plus down to TPN. Now let's look at the
Yeah.
total. TPA plus FNA
Okay.
plus
Okay.
TPB plus FNB. So you see,
Okay.
they are
Yeah.
different.
Yes,
While
I've
in
seen it now.
the precision, so the both of them are not the same. So, but if
Yes.
done, just I think the take-home message here will be the precision, the rows, the recall, the column. So
The
have that
columns.
have that in the back of your mind that on the confusion matrix, the recall will talk about the column of the true positive, false positive. The recall. Then the precision will talk about the true, or you to focus on the true positive, false positive. So it's like this, and this other one is going to be like this. So that's an easy way for you to remember. Okay, so
Thank you.
no problem. So what are the common pitfalls in the model evaluation? I hope I have not passed. Okay, I think we still have a few minutes. So the common pitfalls that you're going to face, because you see, these things are not one-way traffic. It comes with a lot of twerking, a lot of back and forth. You will not have this smooth ride. It's always going to, for you to build a good model. It's not always the rocket science that, sorry, it's almost like a rocket science where you have to do lots of ups and downs, checking. And I tell you, because when you want to deploy this thing in the field, you have to make sure you really know what you're doing. You have to go back and to the drawing board when these things are not working. Because if you don't anticipate this problem, they would escape you when you put them in the field, and then these things will begin to give problems. Now, imagine if you are in area of finance that has to do with things like cryptocurrency or bitcoins. You really want to make sure that the signals that you are getting are the right signals that will earn profit. Not at the end of the day, the person will lose. So you have to make sure the model that you're going to be using to inform decisions when the stockbrokers should invest the money of that is entrusted to them, it won't come back at a loss. They have to make sure what they are doing is right. The same thing if you are in the medical domain, you cannot just deploy anyhow model, because anything you're putting out there has to do with the human lives. So you must make sure that whatever you put out is actually the right thing and is doing the right thing. And I tell you the fact is that because these machine learning models, they are not humans, and they cannot manufacture things, although the generative models, we see them manufacture things via hallucinations. But again, it's the failure where we are unable to give it the right information to process. So that lack of information makes the model to extrapolate and then gives us some information that are not true. So that's why you have to make sure that you don't just put out everything there. So one of the major pitfalls that you would face is ignoring the issues on class imbalances when you are using things like accuracy. Remember, I've talked about this a lot of time because it's something that I've seen it over time. Most of the time when I'm working on multi-class problems, even the binary class problem, one of the issues I struggle to take care of is the issue of these imbalanced classes. Because the class of interest most of the time are rare occurrences. And because they are rare occurrences, the dominant class, which is the negative class instance, will tend to take the lead. And then once the decisions is favoring that class, even when it's supposed to be detecting this other class, because it is underrepresented, you will have problem, especially when you go to the field. And what if there is a distribution shift? Once there is a distribution shift, it means that you will begin to have issues which will likely not just, you're not going to be making type 1 errors, but in this case, you begin to have type 2 errors, which will be very, very costly for you. So always look at the target class. Try to understand if there are imbalances, how do we really take care of these imbalances? How do we make sure that we are not just we're discriminating both positive and negative class instances are very, very important. So in that kind of situation, do not rely only on the accuracy score. Look at the recall, look at the precision, and then remember to look at the F1 score. Then misinterpreting precision recall trade-offs. Like we said, there is a kind of a sort of a tug of war between the precision and the recall. They seems to be on their, this disagreeing, or they seems to be headlocked with each other. So you have to make sure that when you are interpreting it, do not misinterpret them. What is really your model really interested in? Is your model really interested more on the precision, or is it interested on the recall? Is it really interested more on the both? So if it's something that has to do with the both, then you know that the F1 score is likely going to take at the lead. And then whatsoever you're doing, you have to make sure you balance these both matrices. Then over relying on a single matrix instead of a holistic approach, most of the time you don't focus only on one matrices. That's why you have to make sure you look at the confusion matrix, look at the accuracy score, look at the precision, look at the recall, look at the F1 score, look at the macro micro averages, look at the weighted averages, and then you'll be able to know the true state of your model. And then even the ROC AUC curve, you have to look at it to see what is happening. Now, because when you looked at all those things, you can be able to really know. Because you see, all these things we are doing are all have to be built on uncertainty. Because of the uncertainty and the nature, the volatile nature of events unfolding in the real world, we never even model itself. We said it's a simplification of the real world, meaning the real world is complex. So we don't just put everything out there. Everything you have to put out there has to be something that is actually explaining what you are able to capture, the variations you're able to capture. So that doesn't mean you have all the explanation. Like I said, there is no one fit size all approach. But whatsoever you're putting out there should really be that it's addressing a particular gap of interest. So do not rely only on one specific matrix. Rather, look at all these matrices, look at them, and then you could be able to judge which of them make sense. So make sure you have a lot of this at your hands, and then you could be able to say, okay, this is the metrics I should report, and these are what I should go on with. Now, do not ignore the domain-specific question or the testable hypothesis of interest when you are selecting your model matrices. Like I said, look at the matrices that you read, the question you want to answer. For me, for example, in my PhD thesis, I looked at COVID cases where I was predicting COVID-19 severity cases based on genetic data set on the whole exome sequences. So when I was doing such kind of a task, one of the thing that we discovered at first was that the classification handed over from the World Health Organization was around six categories from 0 to 5. So if we are using that kind of categories, it means it's going to be a multi-class problem. But then we discovered that there are situations that are very extreme. There are people that when they get the disease, they are completely, it knocks them out. They have to take them to ICUs. They will require oxygen and all that. And then there are people that even when they cut the disease, they don't react. They are just normal. They do not need oxygen and all that. So when we looked at the classification done, we discovered that, okay, we don't need people in group 1 and 2. We should remove them and focus on the extreme cases, 0 versus people in group 3, 4, and 5. So such kind of model already, the positive class has been given much more priority than the negative class instances. So one of the things I struggled with was that when I was ready to deploy the model in the field, when new data set arrives, I noticed that there is a distribution shift. Now, what I mean by distribution shift, because the new data set was based on a new variant of the COVID. It was not the alpha variants that we trained our model on. So because it was a new variant and some people have already contacted it, so they didn't fall ill, so they were mostly classified as zero. So imagine the original data set I trained my model with there was more of the severe cases than the asymptomatic cases. But when we now have a new data set, there was more asymptomatic cases than the severe cases. So there is a distribution shift. So now I have to now look at the performance of my model to see is my model really robust to be able to adjust to this classification shift, distribution shift, sorry. And then I now begin to think of how and what are the best way to make sure that my model is not just getting the wrong signals. So you have to make sure that whatever you're doing, take into consideration the domain-specific questions that you want to ask to answer. Because, like in my own case, we're not just interested in making prediction or based on this genetic variants or people that are severely ill, but we wanted to detect the genetic variants that are actually making them to fall ill when they get the disease. So those genetic variants, we have to use them now when we identify them to identify target drugs that we could say, okay, probably if you could be able to treat them on these drugs that have already been recognized or repurposed, you could be able to help and treat them and they wouldn't have to proceed to ICUs. So looking at the domain-specific question, it really helps you to be able to answer the question you have in mind. Now, outside some of these that I listed, one of the problems also you are going to face when working with machine learning is that, first of all, machine learning models, most of the time, they ignore interaction. One of the issues they do not focus or talk about is the issues on model causalities. Now, causalities are very, very important. And that's why most of the time, like I said, when you have the data set, try to interact with your data set by making visuals. The EDA section of your exploration is going to actually inform you and give you some ideas on potential interactions or associations that are happening in your data set. So those kind of correlations, you could further zoom into it. Although correlation is not causality. That's one thing you must not forget. But exploring it and understanding these potential associations could really help you to begin to zoom in to say, okay, now what's happening? For example, the fact that somebody smokes does not mean it is a direct express that the person will be down with a lung cancer. But now you are likely maybe to see people that smoke having lung cancer, and it's easy for you to conclude without having to look at some other predispositions that could expose the person to be susceptible to the disease. So you have to make sure you're looking at some of these intricacies, So do not forget, machine learning itself does not imply causality. So you have to make sure you looked at these things with a different statistical model in order for you to establish some of these premises. Then, again, the issue of ignoring dependency. Sometimes you will discover that these futures are not just existing alone. You have to do a lot of building of futures, future engineering. You have to merge some futures. You have to remove some futures. So do not forget that. You can find a situation where one future is the subset of the other futures. So again, during visualization, it could really help you to see some of these things. But again, we also have things like the post hoc model interpretation. Things like Sharp, for example, the Shapley values help us to be able to recognize if there are some sort of dependency in our futures. And even sometimes it could even help us with the future interaction, although it's not a strong point to make our argument, but it's a good start for us to see if there are some interactions happening in our model. Another interesting problem you are likely going to face is the issue of bad model generalization. And again, like we said, the when I told you guys about the confusion matrix, that it's a very good place for you to see how your model is doing. Because if your model is generalizing bad, you're going to really see it from the confusion matrix. And then you could be able to also see it on your AUC ROC curves. Because the AUC, remember, is the true positive rate against the false positive rate. So you could actually see the areas you are confident to make decisions. So by looking at the generalization of your model, you can be able to by looking at the metrics, you could be able to know if your model is going to generalize well. But again, talking about generalization, I was reading a book by Christopher Muller, which one of the person I followed a lot in explainable interpretable AI. I think one of his recent book that he talks about machine learning science or something. Very nice book. The science of machine learning also. I think I need to think about what. But again, the one he stressed on in that book was issues that has to do with trying to perform some sort of external validation on our model. But however, we must be mindful of the distribution shift because, like I told you about my work in my PhD earlier on, that I had that problem because there was a distribution shift. So most of the time, make sure you take into account some of these things when you are having a new data set to validate your model, and then you can be able to know what's happening because uh, um, the potential issue you are going to face is that the new data set you are going to have will not have a label. Because the reason you are developing the machine learning algorithms is to the machine learning models is to be able to validate them on the batches that are coming that do not have labels. So how do you now be able to know what you are doing is actually right? So he provided some point-wise estimation approaches that we could be able to use to see if what we are doing is right or wrong. Because in that case, you are not going to be able to get your accuracy, you are not going to be able to get your ROC curves because you need the true values to be able to plot and see all those matrices. So, but when you have these things and you don't have, you can use the prediction to be able to do that. And then you have to do some sort of um, counter sort of factuals to see if you can be able to distort the process and see how robust the model is doing. But generalization, again, is one thing you must take note of when you build your model. So, one fit all mentality. Very, very, very important. I remember when I was discussing with my panel during my PhD work because every year we defend uh, PhD, what we have done before you move to the next stage. So one of the things I came, I was so excited. Oh, I was feeling so high because of what I've done and all that. So I was so confident. And then one of the professors said, "No, you cannot tell us you are so sure of this because you're not. There could be different ways these things could be approached. So you can't build a lot of surety that this is just the one way. No, there could be several ways that the problem could be approached from. So always be open to ideas, be open to other alternatives and suggestions. Don't just feel that what you have done is the only way. No, like I always say, knowledge is not, we are not in competition. Rather, we want to fill a gap of what we don't understand. So sometimes when you come with that competitive mindset, you will close your mind to your own ideas and feel it's the best. And you could easily discard other people's idea that could potentially help us to understand what we do not understand. So be open to understand that there is no one fit size all approach. Then we talk about overlay complex models. Like I said, try to befriend your data set to really be able to understand if the models that you are using are too complex for your problem or too simplistic to understand the complexity in your data set. So if you don't relate with your data set, make visuals, explore the data set, and all that, you will not be able to know some of those things. And even when you deploy the models, you may not likely get the right thing. For example, convolutional neural networks, excuse me, convolutional neural networks performs well when you have image data set. So I don't think it makes sense using convolutional neural network for a tabular data set. So choices of the model and all that, don't use complex model when for example, if you have sequence data set, You can look at sequence approaches like LSTM, RNN, and so on and so forth, rather than using some approaches that do not match up with it. So understanding your data set will help you to be able to know the complexities that are inside and the models that could help you to approach it. Then ignoring uncertainty, very important, because like I said, one of the problems you're going to face when you deploy your model in the field is that there are so many uncertainties. So you cannot be sure that this model is going to be doing well continuously. So that's why you have to put, maybe sometimes you could say every 3 weeks, every 1 month, every 3 months, you are going to evaluate the model to see if the model is actually on track or the model is not doing well. Because over time, there are uncertainties that could happen and then the model could deviate. For example, diseases these days are becoming resistant, for example, to antibiotics. So it will not make sense if you have a model and you build it on a certain variant of that disease, and then without knowing, just like I told you about the COVID, that the model we developed was built with the alpha variant data set, but later on the disease mutated to beta. It even went to Omicron and all that. So by the time I am to test those things, definitely there will be a distribution shift. And because of some of this uncertainty, you may not have the same performances that you have been having before now. So do not ignore the uncertainty and find a way to quantify the uncertainty. So someone may ask, how do we quantify it? The prediction confidence interval. I think we don't call it confident. I think we call it predictable interval or something. Help us to be able to quantify the confidence and know that if what we are doing is right or not. Then wrong causal interpretation. Remember what I said. Causality is, machine learning most times do not imply causality. So sometimes you have to first evaluate these things with statistical models, and then you could be able to understand the relationship that is happening in your data set. So do not just do some things and imply causalities. However, machine learning is good. It really helps us to get to detect patterns, but these patterns may not imply causality. So be careful about that. Then high dimensional setting. I've talked about that over and over and over again. I told you guys about cost of dimensionality issues, that it's a very big problem. So you don't, be very careful about it, because when issues like sparsity arising due to cost of dimensionality in your data set, it could help in, to make your models perform poorly. So sometimes you have to make sure that when you have this, find a way to see if you could reduce the dimension via feature selection or dimensionality reduction approaches like PCA, then you could be able to. So in a situation maybe the future importance are not quite critical, then you could use the PCA to transform the data set into some sort of linear combination, and then you analyze the pipelines like that. Then you could be able to. So if you are interested in the performance, you may not be interested in seeing which feature is contributing, but in area where interpretability and explanation become critical, you may not be able to follow that route, because the dimensionality reduction approaches are likely going to distort the original features by now transforming them into principal components. So in order for you to take care of them, you cannot use the PCA approaches. So maybe that kind of cases, you now have to introduce things like feature selections. You now begin to think, do you use the future selections approaches that we have there? So I think the next class, I'll talk about the future selection. Then I'll be able to guide you on which of the future selection that you are to use. Are you to use wrappers method, or are you supposed to use the other method? I think there are three approaches to feature selection, but I can't remember the names right now, because most of these things are applied in. But don't worry, by the time I build the learning stuff, the slides, I'll make sure I put those things, so it won't be an issue. So I'll talk about it maybe in the next class, tell you about the feature selection methods we have and how we could be able to use them. And then now I'll be able to tell you more about this lasso, elastic net, and also rich regression penalization approaches. Now, choosing the right matrices. So again, consider the domain-specific requirements when selecting the matrices. Always make sure you consider them. Another thing is resources. Do you have the resources? And the cost of measurement, the statistical visualizations, statistical descriptive statistics, and all that, analysis, safety. You could see so many words are popping out here. High level, strategy, improvement, information, effectiveness, time, understandable scorecard. So many words were popping out. So, but one of the easy way to make this more clear is that look at approaches that are actionable and look at matrices that you could easily interpret them or common interpretation, and then accessible, credible data, transparent, simple calculation, especially issues around transparency is very, very important. So always think in this way, the SMART approaches. Think of it, is it something that can be scalable? Is it something that you could be able to attain or achieve within the specific time period? Do not build your life around these complexities that you have to keep unraveling and all that. Start with the simple, and then you could stack them and build them as you go on. So make sure it is clear the sources of the problem or necessary actions when the matrices goes up, down, flat, or off the target. Then people in the organization recognizes what the matrix mean. That's what they come on into, because most of the time you are not going to be talking to a technical audience. The audience you are going to be talking to are people that do not understand or they are not in your field. For me, for example, as a data scientist in the medical domain, I have to communicate my findings with doctors and other medical experts. So I cannot go about telling them about this precision recon. Maybe some of them will just be interested in specificity and sensitivity. And then, so I have to make sure that I simplify my interpretation to their language so they could be able to understand what I'm doing. So do not build this complexity, because if you're supposed to make the life of the people simple. You're not there to add to make their lives complex. So I so much believe that we shouldn't build this whole, if you are with your peers, you could talk about some of these technicalities, but when you're with people that do not understand this, you just have to make sure you come down to their level, come down from your high horse to make sure you tell them things that they could be able to understand and follow. So make sure the matrices that you're picking are matrices that suits that particular scenario that you are working on. Then transparent, how the matrix is generated, shared, and easy to understand. So make sure that it is transparent. You can share your code so that someone can also see what you're doing. It's not just shrouded in secrecy. You can be able to tell the person how this data set comes on from, how you were able to do that, and also so there is this thing about that we talk about open science. So the whole concept of open science is that you can be able to share your code, your scripts, and everything, your data, so that other scientists could see and try to reproduce what you have done. So, and most of the journals these days, where you submit your manuscripts, they will ask you about these things. So you have to make sure that you have the scripts and the code. Although in the medical domain, sometimes because of privacy concern, you will not want to share some of these data sets. So most of the time, you could tell them, okay, the data set can be gotten on request. So now when the person meets the requirements, you can be able to release the dataset for that person to look at it. So make sure the process which you arrive at your conclusion are transparent, interpretable, and also explainable for people to follow. Then accessible, credible data. Like we said, machine learning works with data, but we know, again, every computer stuff has to do with garbage in, garbage out. So whatever you're feeding the computer, make sure that it is something that you could easily understand, and you could easily, it should be a data set that is clean. Make sure it's not just anyhow data set. So make sure choosing the classification. For example, when you have a balanced data set, you could look at the issues like accuracy and all that. But when it is imbalanced, you could consider things like the F1 score. In regression, you could use the RMSE for penalizing big deviations or error. So I think with this, we have come to the end of our classes, and then I'm open to questions. So if you have any questions, then you could go ahead and we could take care of it. Thank you.
Well, thank you very much for this wonderful session. It's quite informative, and
Thank
it's for
you.
me an eye-opener indeed.
Wow. Wow.
You mentioned I think there are two intriguing things. The sharp, the interpretable model, and feature selection. I was about asking you about feature selections. So because I like in a case where you have let's say 6,000 features and you don't intend to use all the features, is that what? And then you maybe want to use 2,000 features. Is that what you're talking about?
Yes. So again, we are going to talk about those ones as a broader topic on its own, because the feature selection help us to prioritize the most important features. Because when we have a lot of 6,000, you said, it's quite much. And then you can imagine if you don't have the computing power and the resource to be able to do that, that would take almost forever. So you have to make sure that whatsoever you are doing, you are working with the right features. So that's where we now bring in things like feature selection to help us to identify the features that we're supposed to do. But now, when we talk about sharp, most times these are post hoc interpretations. So after we have built the model, we want to now understand by shining a light into the black box to understand why the model made these decisions. So if the model, for example, said this person is not supposed to have COVID, even when the person have COVID, we're interested to know why did the model say this person is not supposed to have COVID? Because the model have its reason. So when you now peep into the model, then you can be able to understand the features that contributes in making the model to say this person do not have COVID. You see, so that's what the sharp does for us. It opens up the decisions of the model and give us the reason and rationales why the model made such decisions. But like I said, I want us to take them gradually. So when we finish the future selection phase, then maybe we could talk about the post hoc, because I want to talk about that and also talk about model deployment, because you need to know how to build the model so you don't get stuck in the Jupyter notebook forever. Because by the time you finish, how do you convert them to scripts, to Python scripts? How do you now build them into web app and all that? So we will go around that route. But like I said, I want to take it gradually. And then also, there is the large language models and deep learning and all that. So I want us to take it gradually as we continue to explore them, to build on this complexity. So the next topic, we will likely look at the future selections, and then we see how we could do the